All right, here we go again. So just want to say sorry for the choppy transitions and things of that nature. Trying out some new software and whatnot, so please just bear with me as we go through the recording process. I'll try to make the videos a little bit longer now. Just trying to make sure that we don't have too big of uploads to do. So anyway, keeping on here. So we have, how are we going to request IP addresses from a pool? So the host is going to provide specific information to the DHCP server during a DHCP request. So specifically MAC address is going to be huge here. Also host name. So a lot of times that we will have our DHCP set to automatically update DNS with your host name so that you can actually resolve your host name to the IP address using DNS, which is a process we'll talk about later in this lecture. Also included in our request is going to be requested lease duration. So like I said before, there are different lease durations for different operating systems, whether that be Linux, whether that be Windows, or whether that be you modifying it intentionally so that you can request a different lease duration. Now, ultimately, the server is going to dictate how long the lease actually is. However, in the DHCP request, we do make a request for a lease duration. If we have an IP address that's currently being used or was previously used on the network, we also might include that to see if it's still available. Obviously, that's advantageous from both a client and a server perspective, because then the server doesn't have to have potentially conflicting DHCP leases for the same MAC address, but also we are making sure that we're trying to keep a consistency where possible on the host. If there are other parameters that are needed, we will send those in the DHCP during the DHCP request process. But ultimately, the four options that are up above that are going to be the most common. So the DHCP server is going to try to make the best IP address, or pick the best IP address possible for that particular host. Now, based on some of the information that we've provided in the DHCP request, then that's what the DHCP server is going to use to give us the best IP address possible. So during the IP addressing process with DHCP, the server is going to be storing IP address mappings in on disk, so in persistent memory, you could say, so that we're ensuring that we're preserving stateful information. So just because a DHCP server might need to reboot, or it may need to, or maybe it crashes, we don't want to have to automatically require every host on the network to request another IP address from the DHCP server. We want to just have business to be able to operate as normal. So that's why we store that information on disk. So I want to take a look at the DHCP and ultimately the BootP message format so we can start getting familiar with how that looks, and then as we get further into the nitty-gritty of the process, we can understand exactly how DHCP is doing what it does. So, again, DHCP extends BootP. And so we are maintaining compatibility between the two. So DHCP can serve BootP clients. However, BootP cannot serve DHCP clients. Now remember, the DHCP extends BootP by adding options. So if you're just on a BootP server, the options aren't going to be available, and therefore it can't serve the DHCP type clients. So it's more of a square is a rectangle, but a rectangle and a square type thing there. So we have the general message format is kind of like the initial portion. This is going to be the fixed length. This is going to be more of the header. And then we have the tail, and this is going to be variable length. This is going to be where our options live. And there's going to be some variations to how we can use certain fields in the header to have more options. but ultimately this is going to be the general message format. And then if you are interested, RFCs that pertain to DHCP specifically are going to be 0951, 1542, and 2131. I believe 1542 is going to be kind of the one that really added the DHCP functionality, and then 2131 circles back and adds a little bit more functionality to it as well. So looking at the different fields that we have that are going to be in the DHCP message format. So we have the operations field, which is going to be 8 bits or 1 byte. And so this is going to be something that determines whether or not this is, or whether this is a request or a reply. And a request is going to have a value of 1, and a reply is going to have a value of 2. And then we have the HW type, or the H type. It's going to be another 8 bits. And then this is going to be assigned based on values that are used with ARP, and they're defined based on ARP parameters. So in most cases, the value that you need to be aware of is 1, which specifies Ethernet, and that's going to be the most common, or very common. And then we have HWLEN, or HLEN, and that's going to be another 8 bits. And so this is going to give the number of bytes that are used to hold the hardware MAC address. 6 is going to be the most common for Ethernet networks, and so basically we're looking at the MAC address having 48 bits or 6 bytes. And so that's going to help us determine exactly how much information we can put in that field. And then we have hops, and so that's going to be another 8 bits. That's going to be where we're storing the number of relays through which the message has traveled. So one thing that we're going to get to later on this lecture is the use of DHCP relays. Now, if you recall, I mentioned that we use broadcast messaging to facilitate the DHCP negotiation process. And so, again, by default, routers are going to drop that type of traffic. So, just briefly, we have the need for a DHCP service or server on each network segment if we use the traditional DHCP process with broadcast messages. Now, that's terribly inefficient because we're not going to have 30, 40 DHCP servers for the various LAN segments at a particular organization, and quite frankly, if it's a larger organization, it could be a lot higher than that. So what we do is we use a DHCP relay to facilitate the process, which uses basically takes a broadcast message. It's going to utilize unicast messaging to forward that onto the DHCP server that has a whole bunch of different IP address pools, and then to basically continue to facilitate that, kind of more like a translator or just an intermediary. And again, we'll talk more about that. But the number of hops is going to be how many relays it goes through. Then we have the transaction ID, which is going to be 32 bits. This is going to be some random number that's chosen by the client, and we're going to use that so that we can keep all these messages straight. So again, this is more of that multiplexing type of scenario where we have a whole bunch of different types of transactions occurring or negotiations occurring all at once, and we need to be able to keep this straight in some way. And so we use the transaction ID to do that. So we're matching our multiple replies and requests together through the transaction ID. And then we have the seconds, which is 16 bits, and that's going to be the number of seconds that have elapsed since the first attempt to establish or renew the address. So just something to keep track of kind of time. Then we have our various flags, which is going to be 16 bits as well. And that's going to basically contain a single bit called the broadcast flag. And we can take a look at the flags a little bit more in the actual header coming up here. But basically, we use this broadcast flag when hosts don't have an IP address and they can't respond to unicast messages. So think about when a host comes on the network for the very first time. The very first time they do that, they're not going to have any network configuration at all, nothing left over, and a lot of times we're going to end up with something like a PIPA address if you're using Windows, or a PIPA in general. And so if we set this broadcast flag, then we know that when we respond back, or when the DHCP server responds back to the client, it needs to do that through broadcast address because it never had a unicast address that can go between networks in the first place. So that flag is there to facilitate that process. Then we have the client IP address, which is going to be 32 bits, as we know already, and it's going to include the current IP address of the requester if we already have one. So, for instance, when we start talking about the renewal process, we're already going to know what IP address we have now, and so we're able to put that IP address in that field if we have it. If we don't have it and it's unknown, then we just set that field to 0. And then we have your IP address, which is 32 bits. So this is going to be filled in by a server when we're providing an IP address to the requesting client. So as we go through this this negotiation process, and I'll show you this here coming up, when we start, or when the DHCP server starts to offer an IP address, that's where we're going to be putting that IP address, is in the your IP address field. Then we have the next server IP address, and that's going to be a 32-bit field as well. That's where we're going to be providing the IP address of the next server to use for the client's bootstrap process, or when we need to download something else. So if there's going to be some other configuration that we need to get from another DHCP or BootP server, we can use the next server IP address. So we're just directing to another server for that process. Then we have the gateway, default gateway or relay IP address. So this is going to be filled in by the DHCP or BootP relays when forwarding messages. So I mentioned before, we are using these relays to cut down on the amount of DHCP servers we have in our environment. When we actually start using these, we're going to fill in the gateway or relay IP address in this field when we're using them. Then we have client hardware address, which is 128 bits. So this is going to be used kind of in various ways. There's going to be more than one that we're going to use this by the server. And the primary function for this is to help us to provide the same IP address each time. So the goal, or the name of the game here, is try to provide as much consistency as possible. And so one way that we're going to do this is we're going to use something like the MAC address. So we're going to fill in this MAC address in our in this field, so that every time we're exchanging these messages, we can see the client hardware address, and then we can provide that same IP address. Again, the name of the game is consistency, and trying to not have variation when possible, simply because it's more efficient. So MAC address was kind of the way that we would do this, especially in the past. And there is a lot to do with the MAC address still, but there also is unique client IDs that are provided. And I think one of the reasons that we're really getting into using client IDs a little bit more is because MAC addresses can be virtualized. So we have a lot of things, a lot of different instances that are using virtual MAC addresses. For instance, VDI. VDI can have different MAC addresses. As a matter of fact, when we talk about even in Windows, with Windows 10, they add the ability when you're on Wi-Fi networks and things to change your MAC address, to virtually change it. So that you're not having the same MAC address, because it adds quote-unquote security for Windows 10. Now that might be true from a home user perspective. I think it's debatable when we are using enterprise type computers, but that's a discussion for a different time. But ultimately, we do use client IDs in place of MAC addresses depending on the system. And then we have our server name, which is going to be the next field, 64 bytes. So it's not always going to be filled in, and it does use ASCII characters. So when we think about that, ASCII characters are going to be 1 byte per character. 63, 64 characters is going to be our main or our limit there. And we'll take a look at some of that here shortly as well. Then we have boot file name, 128 bytes. Again, not always filled in, and this is also ASCII characters. And then we have our options. So remember, this is DHCP only. This is going to be where we get our functionality from a DHCP perspective. We're using those options. So this is what we have for DHCP. So on the left-hand side here, you see that I've outlined the parts that are going to be a fixed size. And so that basically is your BootP. That was the original header that was set in boot P, and that's the same header that we're using today. Now remember, options is where we extended that functionality, and so option 53 in the variable section of options is where we're indicating a DHCP message. So when we're using DHCP, we will always see option 53 as part of that message. And then notice on the right hand side here, I outlined the server host name and the boot file name, which are 64 bytes and 128 bytes respectively. Those are going to be used for kind of an overload area if necessary. So that's our overflow parking lot. If we go through and fill up what's available for options in terms of size, then we can start flowing other options into the server host name and the boot file name as well. Now, if you notice that it does say 16 octets, 64 octets, 128 octets. Octets are just another way of saying byte. So if we go back to kind of IP addressing, we had 4 octets or 4 groups of 8 bits, and 8 bits is a byte. So just wanted to call that out there just to make sure there's no confusion. So DHCP and boot P options. So we're going to talk a little bit about these. Again, this is where DHCP gets its strength. So options are going to be 8-bit tags that indicate the option type. Some options are going to have a fixed size. Some are going to have a variable size. Some of them have 1 byte value indicating the number of bytes for the length. And then the value itself. So there's going to be some variation on how the options are provided in the DHCP message itself. But basically, even though we have the ability to have a lot of different options that are going to be in our DHCP message, we are still only providing kind of a relatively simple configuration for our network devices. For instance, in a lot of cases, we will set up an FTP server or an SFTP server to host our VoIP communication or our VoIP configuration files. So in the DHCP message, we will specify, hey host or hey VoIP phone, this is where you go to get your full configuration. So it's not going to necessarily provide the configuration itself. That would consume quite a bit of the option space. But we are going to say, hey, this is where you need to go to get that. So again, this provides a little bit more of a scalability. This provides a little bit more efficiency for us. And again, as I said before, the options can be overloaded into the server name and boot file name fields if we need to. And those are going to be those last 2 fields there where it's kind of outlined with the bracket in green. So here's some common options, and the way that it's listed here is going to be kind of the option name and then the option value. So we have PAD, subnet mask, router address, DNS server, domain name, requested IP address, address, lease time, and it goes kind of in both columns there. But this is all common stuff that we are going to be using throughout the DHCP process. I mean, we've already talked about some of these that are extremely important, like subnet mask, router address, DNS servers. What are your domain names? These are all important options to have in the message. And then you have things that are kind of core to the DHCP protocol itself. For instance, option number 53, DHCP message type. This is where we're going to be indicating, that it's DHCP and exactly what message type it is. And then we have, DHCP error messages, information about the lease. So these are going to be kind of the most common options that we're going to see, or at least want to be familiar with. So then we have option 53. I want to take a look at this a little bit more, and this is going to be the DHCP message type. So it's a 1 byte long option, and it's always used with DHCP. So we have DHCP discover, DHCP offer, DHCP request, DHCP decline, DHCP ACK, and DHCP NAC. So those are going to be extremely important when we're talking about the DHCP negotiation process. In fact, discover, offer, requests, and acceptance are going to be the core request process when everything goes according to plan. And then you have things like DHCP release, inform, force renew, it's going to be lease query, things of that nature. Other things that are important for the kind of renewal and administration process from a DHCP perspective. So again, very important to this process. But on that left column there, that's going to be where we have a lot of the more core and important options for the protocol. So as I mentioned before, we have this whole DHCP protocol, and we have this main process where we go discover, offer, request, and acceptance or accept. And so the way that you can remember this is Dora the Explorer, I guess you could say. But Dora is how I've always remembered DHCP. So we discover, we offer, we request, and we accept. So discover is going to be from the client perspective. So the DHCP discover option is going to be used, and we are discovering what DHCP servers are available. So we are going to use a broadcast type process, and we'll actually get into the nitty gritty of how the negotiation process goes. But we're going to broadcast out and figure out exactly who's out there. Then the servers that receive that broadcast are going to respond with IP addresses that they can offer, and they're going to be setting the DHCP offer option. And then we as a client then are going to request. We're going to decide which server to use, and then we're going to send an offer to the server, and we're going to inform all the other servers of that choice as well, and we're going to set the DHCP request option. And so then the server, when they receive our request, is either going to accept that, and it's going to determine whether that's still available, and it's going to make sure it's all valid, and then it's going to accept or deny that request through either a DHCP ACK or a DHCP NAC option set in or set for option 53 in our DHCP message. So this is kind of the generally, this is more of a little bit general how we do the negotiation process, or the type of message that we send. So when we're sending from the client, so again, we don't have a network configuration at this point. So when we send, we're going to send it with a source address of 0.0.0.0, and we're going to send this with UDP port 68. And then the destination address is going to be 255, 255, 255, 255, and that's going to be destined to UDP port 67. So even though we don't have an IP address configuration, we do still have the ability through our operating system implementation of our networking stack to use things like 0.0.0.0 and 255, 255, 255, 255, just because those are reserved IP addresses that are used for specific functions. So if we know that we have a DHCP server out there somewhere, or even we think that there could be one out there, then all we got to do is kind of broadcast for it and on that UDP port 67, because we know that's what DHCP listens on from a server perspective. So so we can try to reach our DHCP server that way, or if we're using bootp, I guess we could do that as well. From a server perspective, so there's there's two different ways that we can kind of do this, and we'll take a look at this. We'll see one of these in Wireshark here shortly, but there's kind of an initial, and then there's kind of a for previously configured clients type of configuration. So a source address. As the source address from the server, so it's going to be kind of the server's address on UDP port 67. Remember, UDP port 67 is going to be for DHCP server. And then the destination address is going to be 255, 255, 255 on UDP port 68. So we are going to be sending that. And when we get, I guess you could be thinking, well, if it's 255, 255, 255, 255, which is a broadcast address, everybody's going to receive this. So if you recall, we have the fields that are going to help us kind of keep track of DHCP. And so we have this unique number that's going to be used to track our requests from other people's requests. And so that is how when we receive this broadcasted message back, we're going to be able to determine that it was actually destined for us. Now, in the case of a common or in a previously configured client, we would have the source address from a server perspective be the server address, again, on UDP port 67 for a DHCP server, and then the destination address could be that unicast IP address on UDP port 68. So, for instance, if we are going through the renewal process, we're not going to use the broadcast functionality at that point because we don't need to. We do have an IP address where we're able to communicate on the network, so we can just use that unicast. So this is what the kind of the DORA process would look like from both a client and then the selected server perspective. So we do that discover, we get an offer, we make a request, and we get that acknowledgement. So now one thing that to call it specifically is we get towards the bottom there. We talk about verifying. So we want to make sure, and this is most common, that we check for conflicts. So we use ARP or at least we use protocols like ARP to determine if we have a conflict on the network. Now, if you think about how we could have conflicts, just because DHCP is used in a specific environment does not mean that you cannot set something statically. And so if you receive an IP address from a address pool on a DHCP server and it's valid from a DHCP perspective, but then you have another IP address, or you have that same IP address that's configured on another host, if you actually did an ARP request on the network for your own IP address and some other MAC or some other host responds with a different MAC address, you know that there's a conflict out there. And so typically what will happen is you'll just decline that. And then you'll go through the DHCP negotiation process again and obtain a different IP address that is going to be valid on that network and from that address pool. Okay, so let's take a look at, in depth, the DHCP negotiation process. I want you guys to understand kind of how these the different fields are used, excuse me, as well as just making sure that we understand how this process works. So, first thing, the client is going to broadcast a DHCP discover message. Now, I tried to color code these as best I possibly can. To kind of just call out some of the different pieces that are, the different fields of the different message types, so that we can follow along a little bit easier. So I hope that helps. So we broadcast our DHCP discover message. So all the servers that are going to receive that DHCP discover are going to reply with the DHCP offer message. And this is going to include the offered IP address in the your IP address field. So then in this DHCP offer, we're going to have lease time. And the lease time is going to be denoted by T. And then we're going to have renewal time, which is T1, and a rebinding time, which is going to be T2. So the renewal time is going to indicate the time when the client should try to renew the original IP address that's provided by the DHCP server. And so that's going to be at T divided by 2, or 1/2 T. So, for instance, if your lease time is 8 days, your renewal time is going to be 4 days. So it's going to be half of whatever your lease time is defined as. And then we have a rebinding time. And so the rebinding time is going to indicate when the client should try to renew with any DHCP server. So, for instance, we are going to, at T1, we're going to try to renew with the original DHCP server that we worked with in the past. And then at 7/8 time of the lease time, we're going to just try to renew with any DHCP server. So if we don't get a response when we try to renew at T1, then at T2, we're just going to try any DHCP server. And so this could happen if a DHCP server goes offline. This could happen if there's going to be a new DHCP server. This could happen if we have new address pools and things of that nature. There's different reasons for this happening, but ultimately we have this built-in process to where we are going to say, okay, at T1 we look for the original DHCP server, and at T2 we're going to kind of do a slight panic and just say, hey, any DHCP server, please give me an IP address. And then ultimately we do get some other options that are included in the DHCP offer from the DHCP options list that we looked at in the past. So then the client is going to receive one or more of those DHCP offer messages, and it's going to determine which offer it will accept. And so then the client is going to then broadcast the DHCP request message, and it's going to include the server identifier option. The requested IP address option is going to be set to the IP address that's received in the DHCP offer, and then we have multiple DHCP servers that might receive that DHCP request, but only the server identified in the server identifier option will act and commit that IP address to the client. So this is where, if you recall back, we kind of notify other DHCP servers of what our decision is, and so that's where we do that. We provide the server identifier options so that only that one DHCP server knows that, hey, we chose you to be our DHCP server, and this is the IP address that we want. So after the binding of the IP address is complete and we have that mapping to the IP from the IP address to the client to the hardware address, the server is going to send a DHCP ACK message to the client indicating that, yes, we did ultimately bind the IP address and the configuration can be used. If the server can't bind to the IP address and the DHCP request, for instance, somebody else took it, or an administrator said, nope, that's not part of the lease pool anymore, or any other kind of maybe unlikely scenarios, or just for whatever reason it's not available anymore, the server is going to send a DHCP NAC to the client. And so what's going to happen there is that the client's just going to say, oh, okay, that's too bad, I'll just go through the process again. And it just goes through the whole DORA process again to obtain an IP address. Now, you probably wouldn't even notice this happening overall, just because it's going to happen so fast on the network. But ultimately, for whatever reason, if that IP address is not available, then it will just NAC and then go through the process again. So once the client does receive a DHCP ACK indicating that things are all good to go, it is going to, like I said before, probe the network and ensure there's no IP address conflicts. We're going to use ARP. We're going to use other protocols as necessary to determine if there is an IP address conflict. So if we do discover that there is an IP address conflict, we're going to send a DHCP decline message to the server indicating that we can't use that DHCP message or that DHCP address or IP address. And then we're going to, again, go through the DHCP process again. If a client decides that they want to give up an IP address before its expiration, we can just do a DHCP release to the server and then, again, go through the DHCP negotiation process. And I'll show you that here in just a moment. So the DHCP, the initial DHCP process and the renewal process are very similar. So remember, we have DORA or DORA. In the case of the renewal process, we get to skip the discover and we get to skip the DHCP offer. And so the reason is because we already know what DHCP server we are working with, and we already know what IP address we want to use. So we're going to use our unicast messaging this time, not broadcast messaging, and we're just going to send a DHCP request to the server. And then the server is going to send a DHCP ACK or a DHCP NAC. If it's a DHCP ACK, things are all good to go. If it's a DHCP NAC, then we go through the whole DHCP process again to obtain a new IP address. If the client just needs additional configuration information, we don't necessarily need to renew the IP address, and we can send a DHCP inform. And what that's going to do is it's going to help us just update our configuration. So think of a DHCP inform as simply a DHCP updater. It just updates our configuration. So then remember, from the T values or the time values, this is going to be important for the renewal. So we have T, T1, and T2, the lease time, the renewal time, and the rebinding time, respectively. So the renewal time is going to be at T1, which is going to be 1/2 of T, or T divided by 2. So, again, if it's 8 days, then we start renewing at 4 days. So if we were consistent on the same network all the time, we would just say 8 days is our lease time. Every 4 days, we're going to renew that IP address. And as long as we get those DHCP ACK messages back, we're good to go. We're going to keep that IP address. For a lot of you that work in larger organizations and or even just at home, you can check this and you can see the IP addresses that you have, and you can see you can check it every day, and chances are you're probably going to have the same address all the time, which is helpful. It's helpful from an administration perspective, but it's also helpful from a security perspective. It makes my job easier from an incident response perspective if I can actually say, definitively through DHCP logs that you've had the same IP address for the last month. And so I can be looking for that IP address throughout the environment. But either way, it's just a good thing. It's efficient and it's effective. And then again, the rebinding time is going to be where if we can't get in touch with that original DHCP server, we are going to just renew with any DHCP server. So, okay, so now I want to take a look into Wireshark, and I want to show you some of this DHCP process. I want to show you the full DHCP negotiation process, as well as kind of what releasing an IP address looks like from the Windows command prompt, and then kind of how all of that looks in Wireshark. So if I bounce out of here and head to Wireshark, I am going to start my capture and just verify that it does start collecting packets. Anytime now. There we go. So we got some stuff going on now. So I'm going to head over to the Windows command prompt. And again, I'll just clear out the screen here. So the first thing that I'm going to do is I'm going to do an IP config, and I'm going to release. Okay. What that's going to do is it's going to go through, it's going to release my IP configuration, or my DHCP configuration. Then I'm going to do an IP config, and I'm going to do a renew. And this goes through the DHCP process. So my laptop, my computer is going through and doing the DHCP negotiation process right now. And you see that I did get some information. So if we head back to here, to Wireshark, we can take a look. We can see there's a lot of stuff that kind of went on here. And so if we wanted to search for our DHCP information here, we could just search for DHCP. But remember, it's under boot P and not DHCP. So immediately you can see right away. So we went through this DHCP release process. So we come into here, we can go right into our bootstrap protocol or DHCP, and we can take a look at our various options here. And we can see that we did a, in our options here, option 53, DHCP release, which has a value of 7. So this is our release message. So this was me telling my DHCP server, hey, I don't want this anymore. Okay, and then if you come up here, you can see that was a unicast. That was a unicast from 2.104 to 2.254, which happens to be the DHCP server for the network that I'm on right now. And then if you notice, immediately following that, we go through the DHCP request process. So we go discover, offer, request, and acceptance. So DORA, exactly how we talked about it. And if you notice here, the first source was 0.0.0.0, 255, 255, 255, 255, and that's using a protocol of DHCP. So that's our discover. And then we have, in this case, and this is because of the previous configuration, we have this 2.254, which is the DHCP server, responding to 2.104, which would be this particular computer, saying, here's your offer. And then we have this request, again, going from 0.0.0.0 to 255, 255, 255, 255, using our DHCP ports, saying, hey, can I have this? And then our ACK from the DHCP server to the computer saying, hey, yep, you're good to go. So if we look into this here, we can see that we are going to be using DHCP. And so we have our DHCP option. We see that here, option 53 is discover. And then we have option 61, which is a client identifier. Hardware type Ethernet, client MAC address is there. So you can see that that's going to be the IP address that's there. We have option 50 for a requested IP address, the length of 4, and that's our requested IP address. It matches to what my IP address was before before renewing it through the DHCP process. And then you have host name, which is going to be Synapse Academic. That's the name of this here computer. Vendor class identifier, and then parameter request list. And so you can see that I'm requesting information about subnet mask, router, domain name server, DNS server, domain name, router discover, static routes, things for NetBIOS, domain search, classless static routes, All of these options are things that I'm requesting. These are the requests the options that I'm requesting. And then we do have option 255, which I didn't mention before, but option 255 basically just says end. This is where that ends. So that's a lot of the DHCP process there, or that's a lot of what we go there to take a look at. So here we basically have the header information, and then we get into all the options. So you can see the your client IP address, the next server IP address, relay, all of these are not filled in. They're just set to zeros because we're not using any of those yet. But if we jump down to the offer, now we see that the client IP address is now filled in. The next server and relay agent aren't, because we aren't using those. But then we can jump down into the options again and see now that this is an offer. And then we can see that the server identifier is here, 10.0.2.254. Then we have IP address lease time, which is going to be 2 hours. We have our subnet mask, we have our router, we have our DNS server, we have our domain name, and then again end. So we have all these options that are going to be included there. And then we have, again, our header here that has some of that other information, including our client MAC address, which is going to be our hardware address that we're using there. So then request, again, this is going to be coming from the client. So we get through here. We can see that all of these values are, again, zeroed out. But then we get down into the options and we see request. We can see our client identifier again, and we can see our requested IP address with our server identifier and the fully qualified domain name, and again all of these different information. So this is a request, and it looks very similar to what was provided before. And now we have our DHCP ACK. So everything went great. Everything went according to plan. And now we are getting your client IP address there. We have a lot of the same information, and you see that the type now is DHCP ACK, and then we have our server identifier, subnet mask, all these different options again. So we are just confirming all of that information. Again, the release was there. Remember, bootp is going to be the protocol, and that's going to be how you actually search for DHCP in Wireshark. So that's just something to call out there. And again, if you ever want to kind of figure out what a lot of these pieces look like in the hexadecimal form, you can do that. You can actually figure out what portion of the raw packet data belongs to a specific part of that particular packet. So, all right, we'll continue on in just a moment.